Okay. Again, my name is Mike DeLaCluse. I'm president of Lesman Instrument Company. I'd like to thank everybody for taking the time out of their busiest schedules to join us for today's webinar, Flame Safety 101. This is going to be the first in a series of sessions covering the topic of flame safety, with a couple more to follow in February and March. So if you like what you hear today, plan on attending our next session, which will be in February, and we will get some announcements out as we get that date established. Today's presenter is Dave Shunn. Dave's Regional Sales Manager for Fireye, with responsibilities for distribution and OEM customers in the Midwest. Dave has over 30 years of experience dedicated to flame safety, having worked for manufacturers and distributors of both controls and burners. When with customers, he helps with troubleshooting, startup assistance, and incident investigation. You'll find Dave's style light and lively with an emphasis on the practical. Today we might find him a little flat because he's suffering from a little bit of the flu. Because of the large number of attendees, we will be muting the phone lines. If you have questions, there is a chat tool down in the lower portion of the GoToWebinar tool section that allows you to type in questions. So please go ahead and type those in, and I'll get them answered as they come in. With that, I'm going to turn it over to Dave, and Dave will take it away.
Hey guys, thanks for your time. I appreciate it. Mike already made my excuse for me, so I do apologize. Don't get too close to your monitors, or you too might get the flu. So, this is a basic course. We're going to start out just with the basics. If you're an experienced guy, might be the wrong course for you. But anyway, away we go. Okay, what's a flame safeguard do? Number one, it sequences the operation of the burner to conform to existing codes, supervises the flame, guards against unsafe conditions based on the inputs that it gets through auxiliary devices, such as high and low gas pressure switches, and performs a safe start check. In the past, that was relay logic. Nowadays, with microprocessors, it checks the status of the inputs and outputs, and it provides checking to itself to make sure there are no issues going on. Here's a typical boiler. You've got your burner, your flame scanner. You have a main valve train and a pilot valve train. A set of controls, operating, modulating, high limit, any auxiliaries. Most boilers have a low water cutoff and an auxiliary low water cutoff. This is a picture of an IC burner, D series, on a looks like a Superior boiler. You can see that they have a rotary damper, so you've got a mod motor. That mod motor is connected to the air, and by linkage connected to the butterfly valve. You also see an airflow switch and a pilot valve in there. Here's a nasty old piping situation with a couple of Honeywell valves and actuators, D4055. So you've got double block and bleed, which is pretty much an industry standard. You have an upstream and a downstream valve and a normally open vent valve. The theory being that if the upstream valve is leaking, the gases will be exhausted up through the vent pipe to the roof. Typical inputs to any flame safeguard excuse me, will be power, the controller, your flame signal, any limits, and interlocks. Typical outputs will be a burner motor, ignition transformer, pilot valve, main valve, modulation circuit on some, and alarm. And for you service guys, that is the money switch. Let's talk about a couple of basic terms so we're all on the same page. We start out with pre-purge, and that is blowing air through the combustion chamber prior to the start of the ignition sequence. Codes which require a minimum of 4 air changes based on the size of the vessel. Post-purge is blowing the products of combustion out of the combustion chamber after the call for heat has ended. A limit is a high or low minimum standard it must meet, such as high and low gas pressure switches, low water cutoffs. An operating control is the control that is going to initiate the call for heat. Could be a temperature sensor, a pressure sensor, or a PLC. A start interlock is an interlock that must be made prior to the start of the ignition sequence. A valve triple closure switch is an example. A running interlock is an interlock that must make and stay made during the entire call for heat, such as an airflow switch. Excuse me now. So sorry. There are 3 modes of reaction that flame safeguard controls have for the loss of main flame. In the old days, and you don't see much of it anymore, was relight. Relight said, when I lose the main flame, I will immediately go back to pilot and ignition. That would be a Fireye UVM, TFM type control, old Honeywell RA890, 7890 type controls. More common are the following 2. One is recycle. Recycle says, hey, I lost my main flame. Let's go back and do a pre-purge and then light the pilot and then try to relight the main. A non-recycle or a lockout type control says, hey, I lost my main flame. This is a big deal. I need a person to come here and see what's going on and then reset. Pilots come in 3 flavors as well. Very seldom seen are standing or continuous pilots. Those are most likely found on cast iron sectionals in low-rise type office space. Intermittent comes on, stays on during the entire call for heat, and the safest form is interrupted. That comes on, lights the main, and then it drops out. That way you know that your flame sensor is looking at the main flame and not being tricked by a pilot. This is This is the most important slide. If you want to go to sleep after this, great. But if you take this slide home and you understand the sequence, you can troubleshoot any flame safeguard control. And I don't care if it's a red box or a blue box. I don't care if it's on a rooftop or a boiler or a process oven. Based on codes, all flame safeguard is going to go ahead and follow this sequence. And if you have a good understanding of what auxiliary devices are activated during the sequence, you'll be miles ahead. First one, standby. Standby, there is no call for heat. The operating control has not activated, so the flame safeguard is just resting. Second is the call for heat. You're only going to get a call for heat when the operating control closes and all interlocks are made. If you got a cold building and your flame safeguard is not activated, your boiler or burner's not running, then you go look at your operating control. You go look at your interlocks, high and low gas pressure switches, low water cutoff, high limit, and so on. Then does a safe start check. The control is going to look at the status of the inputs and outputs. Next, we have a pre-purge. What happens during pre-purge is the flame safeguard turns on the burner motor, but it doesn't know what's going on until an airflow switch tells it, yes, the burner motor is running and everything is fine. So if you're locking out at pre-purge, locking out at pre-purge, you know to check the airflow switch, check the motor starter, and away we go. Next step is pilot trial for ignition. During pilot trial for ignition, you're going to open up a pilot solenoid. You're going to have an ignition transformer send a spark out, and you're going to have a flame scanner tell the flame safeguard that you've got fire. So if you always always lock out of PTFI. You want to check the scanner, the pilot gas pressure, and ignition transformer. Then we open up the main valve, and we go into auto or modulation, where the controller controls the firing rate. We end the call when the operating control opens, and then we do a post-purge. Any questions on that?
We do not have any questions on that at this point, Dave.
Okay, I'm glad to hear there's life out there, because there's barely life in here. Okay, we at Fireye are so smart. We know that fire is hot. We also know that it expands the gases. There are byproducts, and there is ionization in and around the flame, and that it emits radiation in 3 forms: visible light, infrared, and ultraviolet. Back in the 30s, some smart guy invented flame rods, and he said, you know what, I can shoot electricity through that flame, so when there's a flame, it's like a light switch being made, and the circuit is closed. And when there is no flame, the circuit is open. The problem with that was that if you had a high-resistance short to ground through a cracked ceramic or broken insulation on wiring, the control couldn't tell whether there was a flame or no flame. So then some smarter guy said, you know what, I can do rectification. Rectification, if you think of the sine wave, is like an S laying on its side, and so you have alternating current. Okay, so you have half of that wave above an imaginary line, half of that wave below it. So in rectification, the smart guy said, you know, if I have a 4-to-1 ratio of ground to flame rod, I can rectify that so it looks like a direct current. I'm only going to have half of that sine wave. That's kind of like me and my politically incorrect shotgun shooting at the side of a barn. When I shoot the side of that barn, almost all the pellets are going to hit that. In a flame rod, that's like the current going from rod to ground. Almost all the electrons are going to hit the ground surface. Now, if I go out with my friends and I try and shoot that elusive little bunny rabbit, I'll be lucky if a couple of my pellets hit that hit the bunny. And that's an analogy to the ground surface going to the rod. Very few electrons are going to hit the rod. So now we've taken an AC sine wave and converted it to a DC. The amplifiers in modern-day controls are designed to accept that DC current. If they get a full AC, they'll lock out. Common problems with flame rods are corrosion in and around the ground surface, cracked ceramics, wiring insulation broken down, moisture, sometimes improper location or ignition interference. How do you correct that? Make sure there's a sufficient ground area, make sure your connections are tight, make sure there's no corrosion. Unless the guy in front of you screwed it up, typically the igniter rod and the flame rod will be on opposite sides of the burner. And then you also want to check the ignition rod and make sure it has the proper spacing. Look at the manufacturer's recommendations. But a good rule of thumb for a 6,000 volt secondary is a 1/16 of an inch, 10,000 volts, 1/8 of an inch.
Hey, Dave.
Pardon?
We did have a question in there. There was a acronym thrown out, MTFI. What is MTFI? I didn't catch that one.
I'm sorry. That is main trial for ignition. Typically, in any burner sequence, you're going to have a pilot trial for ignition. During that time, it is either 5 or 10 seconds. You're going to open up a pilot valve and throw spark in there. We call that unsupervised because it's a timed sequence, either 5 or 10 seconds. After you light the pilot and you prove it through your flame detector, then you go to MTFI, which is main trial for ignition. And that is a supervised event in that if for some reason you lose flame signal, you will lock out based on the flame failure response time, which by code is nominally 0.8 or 3 seconds, depending upon the device. Good?
Very good. Thank you.
Okay. How come you get to see the questions and I don't? Okay.
It's like being the man. It's like being the man behind the curtain.
I see. Wizard of Oz. Okay. Optical detectors, men. Photocells, infrared, and ultraviolet. There's a little chart that shows you that UV is found in gas flames. It's also found in oil. It's found in hot refractory. And not in that line is ignition spark. You can see that oil and coal are very rich in infrared, not so rich in ultraviolet. Typically, UV is less than 1% of a flame. It's normally found in the first third, and IR is plentiful in a flame. When we use an optical detector, we want to go through the throat of the burner. That's where the flame is actually locked onto the burner head. And by using the angle shown on the slide, you can see that we can pick up both UV and IR wavelengths. A rectifying photocell is not found very often anymore, but it's based on the same principle as a flame rod. The cathode is coated and the anode is not, so we can shoot electrodes in one direction but not the other one. And that rectifies the alternating current sine wave. Fireye 48PT2 infrared detectors look for low frequency flicker signals used on gas and light oil. You put a whopping 7 volts DC on those. Normal resistance is 20,000 to 80,000 ohms. I don't know what Honeywell's is, but Mike, you could probably tell the guys the troubleshooting principle is going to be the same, but there's different resistance. In the presence of infrared, resistance is reduced and it allows the current to pass. If you want to troubleshoot a Fireye infrared scanner, if the cell has been removed from a working burner, and I don't know why, because if it's working, you're not there. You're somewhere else where there's a problem. But you would want to let it stabilize for about 5 minutes. Normal resistance is 35 to 40,000 ohms. You take a flashlight, not an LED flashlight, but standard old school type flashlight, hold it about a foot away, and just shake it back and forth in front of it. While you're doing that, you have your meter connected and you check its resistance. Pardon me, if it drops below 5,000 ohms, the cell should be replaced. Any questions on IR scanner troubleshooting? The next session, we're going to get into detailed sequences, and we can go into that. Yes. Sorry, Mike. Was there a question or no questions?
No, no questions. We're good.
Okay. UV scanners. UV are quartz-filled tubes. There's generally an inert gas in there, either nitrogen or argon. Fireye puts 560 volts on it. We look to the middle, deep to deep UV. So we look at 190 to 270 nanometers. Typically used on lace gases, number 2 oil, peat bog, natural LP. It's a picture of a Fireye UV1A3 for 3 foot, UV1A6 for 6 foot. UV scanners can fail in 2 modes. One is a runaway mode, the other is a no signal mode. If you have no signal, you want to close and secure the fuel valve. You want to pull that scanner off, and if you're doing a start check for the fall on a heating type appliance, then you want to make sure the spiders haven't moved in, there's no debris or dirt, so the scanner has a clear view. On a Fireye control, we'll check S1 and S2, make sure there's 560 to 610 volts. If you don't have that voltage there, go to L1 and L2, make sure you're getting 120 volts. If the voltage is okay, you want to, again, make sure your manual fuel cock is turned off. You want to remove the scanner, and you want to get a BIC ultraviolet generator. Those are found at Walgreens and CVS, as in Bic lighter or a torch. Hold that torch in front of it and see if you get a flame signal at the control. If you have no signal, check the continuity of the lead. If you still have a problem, de-energize the control, remove the scanner, and power it up. The control should cycle all the way to PTFI, pilot trial for ignition. If the voltage on S1 and S2 is okay, it's most likely the scanner. If that voltage is low, it's probably part of the amplifier network, so you'd want to replace that. If you have a false flame signal, the control is not going to start. Make sure your voltages are correct. Make sure the limits and operating control are calling for heat. Disconnect the scanner. See if you can get the pilot trial for ignition. If you can, reconnect the scanner. Make sure it's run in separate conduit. And look at the tube. If you see a blue-orange glow in the tube, that is a condition called a runaway tube, and at that point the scanner needs to be replaced. Because runaway tubes are a characteristic of ultraviolet scanners, codes require that any appliance that runs for 24 hours or more continuously needs a self-check scanner. A self-check scanner has a shutter. That shutter closes for about half a second, stays open for approximately 4 seconds, and it produces a chopped signal. The amplifier network is designed to accept a chopped signal only. If it gets no signal or a continuous signal, it will lock out. Again, make sure all the fuel valves are closed. Check the proper voltage, L1 and L2, 120 nominally, 560 at S1 and S2, and 120 volts at the black shutter leads. If the shutter fails, the system will always lock out in PTFI because the shutter fails in a closed position. Visually check the shutter. You can hear our shutters click about every 4 seconds. You can also shine a flashlight down there and see the shutter physically block the view. We used to say replace the scanner but save the tube. I don't believe in that. If your shutter's crapping out, then your tube's next, so replace the entire scanner. If you have a false flame, remove the scanner and cover it. Restart the control. It won't restart if it's connected because it's showing a false flame. You'll see the flame light will be on the control, and or through the display you'll be getting a flame signal. If there is no signal, get out your BIC again and hold that in front of the scanner. If you still don't get a signal, make sure the continuity of the wiring is correct, and then replace the scanner. UV,
hey, Dave.
Yes.
One of the questions we had come up, are all IR and UV scanners self-checking?
No. UV scanners can either be self-check or non-self-check. Non-self-check will be a Fireye UV1A3 for a 3-foot lead, UV1A6 for a 6-foot lead. Honeywell, I think it's C7027 mini peepers. Those are non-self-check.
Right.
A self-check type scanner would be a Honeywell purple peeper or a Fireye 45 UV5, and those are larger physically in size and are required by code if the appliance runs 24 hours or more. Infrared scanners, which is the Fireye 48 PT2, and I can't remember off the top of my head the Honeywell number, but do you remember that, Mike? Do you know what that is, top of your head?
Not off the top of my head, no.
Yeah. Anyway, infrared scanners are inherently fail-safe, and I'm not sure about the other guys, but we make a what we call an auto-check amplifier for infrared, and that checks its amplification network, but a IR scanner will always fail to the safe mode, open, no flame signal. If you use it with our auto-check amplifier, it's the same as using a UV self-check and is rated for 24 hours continuous operation. Not sure what the other guys do.
Hey, Dave.
Answered? We good?
We got another question too. Is the output of the UV scanner a voltage or a current?
Voltage or
current? Really, the question is, what's the output of a UV scanner?
In basic commercial controls, it completes a circuit, so it's voltage. In our advanced controls and smart scanners, where we use on power plants and petrochem and all that, we actually send back a pulse on signal. We look at 21 different flicker frequencies, and it's more involved. Okay, UV, unobstructed view of the flame, must not sight ignition spark. We can wire two non-self-check in parallel. We can also, Fireye has a shutter drive kit and a scanner that doesn't have shutters in it, so we can also do self-check scanners in parallel. Again, the sequence, most important slide of today. Standby. The controller is not called for heat. Call for heat only happens when the controller is closed and all your limits are made. Safe start check, where the control monitors its inputs and outputs. Pre-purge, blowing air through the combustion chamber. We got an airflow switch telling us we've done it. Blower motor, motor starter. Pilot trowel for ignition. We're opening up a pilot valve. We're throwing spark in there, and we're looking for a flame detector to give us feedback. Main trowel for ignition. After the pilot has established and proven, then we open the main gas valves and light off. We then modulate until the call for heat is satisfied. The controller opens. We end the call, and we do a post-purge to remove the products of combustion. Primary controls that we'll get into in future sessions would be Fireye UVM TFN, our M Series 2, and our Micro M. Those are non-modulating controls, very basic inputs and outputs. You see operating control and limits come in through terminal 7. We prove an airflow switch. We prove flame signal. And then your basic outputs, pilot, main, ignition, burner motor, and the money terminal alarm. Excuse me. Programming controls are Fireye's old T-Series, which was tube type. The D-Series, the flame monitor, the E110, and now the burner logic. Inputs on those are operating controls, fuel valve proof of closure, running interlocks, high fire purge interlock, low fire start switch. And outputs blower, ignition, pilot, main, alarm, and modulation circuit. So that's the basic overview of flame safeguard. Any questions?
We do have a question here. You can prove correct operation of a UV scanner with a BIC, but how do you verify correct operation of a flame rod?
Flame rod is either going to have a signal or not have a signal. A flame rod will typically fail to the safe mode where you get no signal. If you're getting no signal, what you need to do is visually inspect the flame rod, make sure that the ceramic is not cracked or there's not moisture on it. Make sure that the wiring is proper, not shorted out anywhere. The insulation is still good on it. If you still get no flame signal on that, then you should bring the control into Lesman to put on a tester. They can test the operation of the control, make sure it's proper. Because I take my controls nowhere else but Lesman, by golly.
Thanks, Dave. That is the last question we have, unless anybody else has one and wants to send one to me. I'm watching the question pane here to make sure that we're not missing any. If no more come in here in the next few seconds, Dave, I'd like to thank you very much for the presentation. If anybody out there in the audience does have any specific application questions, feel free to give us a call at 800-9-LESMAN or 800-953-7626. If you don't know your account manager, just feel free to ask for me, Mike DeLaCluse, and I'll make sure that you get taken care of. As I mentioned, in the next few months, we will be hosting 2 more sessions regarding flame safety. We will get announcements on those out before it happens, so you will have the opportunity to sign up and sit in. If you would like to show this presentation to anyone else, it will be found and posted on the Lesman website shortly. We have a tab there called Training, and it will be posted under that. Again, there aren't any more questions. So, Dave, thank you very much for your time. And at this point, we'll end the session.
Great. Thanks, guys. Have a great weekend. Bye.
You too, Dave.